Hello, my name is Faslul Rahman. This is my Unit-3 mid-unit assignment for MHF4U. So let's start with question number 1. Question number 1 asks us to describe what happens to the domain and the range of a logarithmic function under a vertical reflection. Support your explanation with diagrams. So when a logarithmic function is reflected vertically, the domain and the range of the function remain the same. However, the graph of the function is reflected across the x-axis. Let's consider a logarithmic function y equal log ax. The domain of this function is all positive real numbers and the range is all real numbers. So now let's consider the graph for this. So this is the graph. Here's the domain and the range. Let's discuss it below. So graph 1, y equal log ax, the original logarithmic function. Shape. First one is the shape. The graph of y equal log ax is a curve that approaches but never intersects the x-axis. It has an asymptote along the x-axis, which means that the curve gets infinity close to the x-axis as x approaches 0, but never actually touches it. So here we can see this. The second one is the direction. The curve of the graph rises steeply as x approaches 0 from the right, then gradually levels off as x increases. The third one is the domain. As mentioned earlier, the domain of y equal log ax consists of all positive real numbers. It does not include 0 or any negative values of x. Therefore, the domain is x is an element of R and x is greater than 0. The fourth one is range. The range of y equal log ax includes all real numbers. This means that the function can take any positive or negative value, including 0. So when we reflect the graph 1 vertically, we get a new graph that is a reflection of the original graph across the x-axis. The new graph is represented by y equal minus log ax. Also, the domain and the range of this new function are still all positive real numbers and all real numbers respectively. Now let's consider the new graph. So this is the new graph. So graph 2 minus log ax vertically reflected logarithmic function. First one, we are going to discuss the shape when we apply a vertical reflection to y equal log ax to create y equal minus log ax. The shape of the graph changes. It is still a curve, but now opens downwards instead of upwards. So here it's opening downwards. Above it's opening upwards. So instead of upwards, this reflection flips the original graph over the x-axis. Second one is the direction. Unlike the original graph, the reflected graph of y equal minus log ax starts high on the left side and gradually decreases as x increases. So here we can see. Third one is the domain. The domain of this graph remains the same, consisting of all positive real numbers, which is x is greater than 0, just like the original function. Therefore, the domain equal to x is an element of R and x is greater than 0. Fourth one is the range. The range also remains the same. It includes all real numbers, both positive and negative, as in the original function. Therefore, the range equal to y is an element of R. Finally, comparison and conclusion. In this scenario, when comparing the two graphs, we observe that the main difference between them is their shape. In the original logarithmic function, y equal log ax opens upward, while the vertically reflected function y equal minus log ax opens downward. However, with the same domain and range, they share the same set of input value, which is X values, and produce the same set of output, which is Y values. Therefore, in conclusion, we can say that when a logarithmic function is reflected vertically, the domain and range of the function remain the same. So we discussed the question number 1. Let's move on to the question number 2. Question number 2 asks us to describe what happens to the domain and range of a logarithmic function under a both horizontal and vertical translation. Support your explanation with diagrams. For this, let's start with the logarithmic function graph of the form y equal log ax. So here is the graph, here is the domain and the range. So let's start with horizontal translation. So horizontal translation refers to shifting the graph of a function horizontally, which is left or right along the x-axis. For the logarithmic function y equal log ax, a horizontal translation can be expressed as y equal log a within bracket x plus d, or y equal log a within bracket x minus d, where d is the amount of translation. So first one is if d is positive, it shifts the graph to the left. Second one is if d is negative, it shifts the graph to the right. For example, if we shift the graph right by d units, we express it as y equal log a within bracket x minus d. This means every point on the graph is moved d units to the right. Below we can observe the graph. The graph is moved d units to the right. So here is the domain and the range. We will discuss it below. First one is the domain. The domain of the translated function y equal log a within bracket x minus d is x is greater than d, given the new vertical asymptote at x equal d. Here we can see the vertical asymptote at x equal d. This means the function is defined for all values of x greater than d, or we can say it is defined for any real numbers greater than d. Therefore, the domain is x is an element of R and x is greater than 0. The second one is the range. The range of this function can be any real numbers, which means there are no restrictions on the range. Therefore, the range is y is an element of R. So let's discuss the asymptote. Earlier vertical asymptote. For the original logarithmic function y equal log ax, the vertical asymptote is always at x equals 0. So it's always at x equals 0, the vertical asymptote. Current vertical asymptote. In the translated function y equal log a within bracket x minus d, the vertical asymptote has indeed moved to the right by d units and is now located at x equal d. We can see here it is moved. So therefore, we can say that when horizontally translating a logarithmic function to the right, the domain changes to x greater than d, but the range remains unaffected, remaining as all real numbers. Next, let's move on to the vertical translation. Vertical translation involves shifting the graph of a function vertically, which is up or down along the y-axis. For the function y equal log a x minus d within bracket, a vertical translation can be expressed as y equal log a within bracket x minus d plus b, or y equal log a within bracket x minus d minus b, where b is the amount of translation. If b is positive, it shifts the graph upward. If b is negative, it shifts the graph downward. For example, if we shift the graph if we shift the graph vertically by b units, we express it as y equal log a within bracket x minus d plus b. This means every point on the graph is moved b units upward. Below we can observe the graph. Every point on the graph is moved b units upward. Here is the domain and the range. First one, domains remains unchanged. The domain of the function remains x is greater than d, unaffected by the vertical translation. Therefore, the domain is x is an element of R and x is greater than d. Range remains unchanged. The range of the function remains the same, which is all real numbers. The vertical translation does not alter the possible output values of the function. Therefore, the range is y is an element of R. Graph shift upward. The entire graph shift upward by b units due to the vertical translation. Here we can observe it. So, to conclude, we can say when performing a vertical translation upward, the domain and range of the function remains the same. So we are done with question number 2. Let's move on to question number 3. Question number 3 asks us to graph the function fx equal half log x minus 4. There are 4 parts A, B, C, D. Let's discuss it. So question number 3. First, let's graph the basic logarithmic function fx equal log x as reference point. This function has no shifts or transformation and it looks like this. We can see the graph. Now let's analyze the transformation that occurs in our original function fx equal half log x minus 4. Transformation 1, vertical stretch by half. This half. The first transformation is a vertical stretch by a factor of half. This means that each y coordinate is multiplied by half. Transformation 2, vertical stretch down by 4. This minus 4. The second transformation is a vertical shift downward by 4 units. This means that each point on the graph is moved down by 4 units. The graph for fx equal half log x minus 4 is in the next page. So here we can see the graph fx equal half log x minus 4. So part A asks us to draw the graph. So A says graph the line y equal x on the same grid. So part A. In this part, we will graph the line y equal x on the same grid where we have plotted the function fx equal half log x minus 4. Let's start by graphing the line y equal x. This is a fundamental linear function with a slope of 1 and y-intercept of 0. As we can see, the line y equal x passes through the origin, which is 0, 0, 0. So we can see it passes through the origin y equal x, the line. So let's move on to the B part. B part is graph the inverse function f inverse x by reflecting fx in the line y equal x. So B part, to graph the inverse function f inverse x, we start by reflecting the graph of fx in the line y equal x. This reflection swaps the roles of x and y for each point on the graph. As we can see, every point on the original graph of fx has been reflected across the line y equal x to obtain the f inverse x. So next we'll discuss the asymptote, horizontal and vertical asymptote. In the case of f inverse x, when x approaches positive or negative infinity, the function approaches the value of 4, which means the horizontal asymptote is y equal 4. So here we can see the horizontal asymptote is y equal 4. The vertical asymptote for f inverse x is x equal 0. And here we can see the vertical asymptote is x equal 0. So let's move on to the C part. Determine the domain, range, and the equation of the asymptote of f inverse x. So C part, domain of f inverse x. The domain of f inverse x is determined by the range of the original function fx after reflecting across the line y equal x. We found earlier that the range of fx is all real numbers because it's basic logarithmic function without It is a basic logarithmic function without any vertical stretches or shifts. When we reflect the graph of fx across the line y equal x, the x values become the y values and vice versa. This means that the domain of f inverse x will also be all real numbers. But in terms of x values, it corresponds to x less than 0. Next one is the range of S inverse x. As we discussed above, when we reflect the graph fx across the line y equal x, the x values become the y values and vice versa. This means that the range of f inverse x will also be all real numbers, but in terms of y values, it corresponds to y greater than 4. To sum up, the domain of f inverse x is less than 0, meaning it is defined for all x values less than 0. Therefore, the domain is x is an element of R and x is less than 0. The range of f inverse x is y greater than 4, meaning it can produce any y value greater than 4. Therefore, the range is y is an element of R and y is greater than 4. So here we will look at how to determine the asymptote equation. To find the horizontal asymptote for f inverse x, we need to determine the value that the function approaches as x goes to positive or negative infinity. In the case of f inverse x, when x approaches positive or negative infinity, the function approaches the value of 4, which means the horizontal asymptote is y equal 4. Therefore, the correct equation of asymptote is y equal 4 as the function approaches this value as x goes to positive or negative infinity. So we are done with part C also. Let's move on to the D part. D part asks us to determine an equation for f inverse x. This is our final question. D part. So step 1 asks us to start with fx. We begin with the original function fx equal half log x minus 4. Step 2, swap x and y. To find the inverse, we switch the roles of x and y. Here it is. Step 3, isolate log y. Next, we isolate the term containing log y. Here it is. Step 4, eliminate the fraction. To eliminate the fraction half, we can multiply both sides by 2. So here I have done it. Step 5, remove the logarithm. To get y by itself, we need to remove the logarithm. This can be done by exponentiating both sides. Since the base of the logarithm is 10, we will use 10 as the base. So 10 to the power 2 within bracket x plus 4 equal y. Step 6 is to simplify. Now we simplify the equation, which is y equal 10 to the power 2 within bracket x plus 4. So y equal 10 to the power 2 x plus 8. Step 7, final equation. The equation for the inverse function f inverse x is f inverse x equal to 10 to the power 2x plus 8. So this is our end of our assignment. So thank you for watching. Cheers.